Okay, in number 13 here, our base is defined just by two functions right here. Y is equal to x squared and y is equal to 3. Usually there's like 3 functions that give you the border here, but I think pretty quickly we're going to look at this one and we're going to be able to understand what's going on here. So I'll go ahead and while I have the black pen out here, I'll just get this thing set up in terms of what our graphs are going to look like. And so what's going on here, guys? We have a regular parabola here centered, with its vertex at the origin opening upward. So that's y equals x squared, not very well drawn. And then the line y equals 3 is going to be a horizontal line right here. And so, yeah, that does fence off one particular region here, guys. So this that I'm kind of shading in yellow right here is going to give us the concrete foundation that we're going to pour. And then what are we doing? I'm reading again now. We're going to build squares out of this that run perpendicular to the y-axis. So our squares are going to go something like this from side to side here. And that red segment that I just drew is one side of our square. So I'll go ahead and call that an S. Now, you really don't need the second graph here, but if you wanted it, okay, your parabola would kind of look something like this. There you go. Then there's this horizontal line cutting across it like that. So if you wanted to, again, you shade in the concrete base, and there we go. And once more here, that side of the square runs perpendicular to the y-axis. So that would be S. And we're now going to build a square sticking up in the air out of that. All right, that's what's going on right here to construct this solid. So let's start with something obvious that we know, everybody. Our cross sections are squares, and the area of a square is simply equal to its side length squared. But what we need to figure out, and I could have done this earlier, as soon as we see here that our cross sections are running perpendicular to the y-axis, that tells us that this is a dy problem. That means that every equation that we have that's solved for y needs to be turned around and solved for x. So luckily, that one's pretty easy to do here, guys. You just take the square root of both sides and get x equals plus or minus the square root of y. Now, each half of this parabola is one of those two equations there. The one on the right is the positive square root of y, and the one on the left is x equals the negative square root of y. So what I would do now is try to get S, the length of this piece right here, represented in terms of y. So S is going to be right curve minus left curve, the square root of y minus the negative square root of y, which of course then means that S is just going to be 2 root y. So back to where I was just a second ago, area now expressed as a function of y is your side 2 root y squared. Okay, and we'll square both the 2 and the root y and end up with a 4y for the area of any one of those squares. And of course, we're drawing an infinite number of them as we move along here. Okay, so now here should be the relatively easy part. The volume of this region is going to be a definite integral. We know that it's going to be taken with respect to y. The integrand is just your a of y expression, which is a 4y. I guess I didn't need to leave that much space. And the limits of integration are the lowest and highest values of y. This thing begins when y is 0 and ends right up here. Oh, that's why I was given that, when y is equal to 3. You'll notice we hadn't used that 3 at all yet up until this point. Okay, so now that we have that, I don't think this integral is going to be too tough to evaluate by hand. That's going to be a 2y squared for that antiderivative, evaluated from 0 to 3. So yeah, not bad at all, guys. That's a 2 times a 9. That's going to be an 18 minus the 2 times the 0 is 0. And it looks like we're going to end up with 18 cubic units for the volume of this solid here in problem number 13.